clicked on it, but okay. Yeah, that's true, huh? That's strange, but why that? Okay, well then let's start again, but then I will do it very short. Sorry for that. I think now the meeting started and I start already the recording of it. Sorry, I made somehow a mistake with not starting the webinar before. Sorry to confuse you. I hope now everything is working properly. But as I know, I think I'm still shared with the presentation. So let's go back very quickly to the program, and yeah, let's announce once again the 6th annual conference at Tatwiller in Altdorf. The program will be disclosed early next week on the website, the final program with all the speakers. So have a look on our website. Please register. Registration is open. We're looking forward to meet all the battery iBAT community in Altdorf. And I would also like to advertise the Circubat conference in Bern in the Neue Festhalle in November. Also there you find the information on our website. What is new, because we have a dense program with Swiss Battery Days, annual conference, and Circubat conference in the second half of this year. We decided not to do a workshop this year. Would basically overload the program, and therefore we say let's start early next year with a workshop about automation and robotics at Brucker in Fellanden in most likely end of January, maybe early February, and the second workshop at FlexSpace in where is it? Regensburg? No, how is it called? Laufenburg, in Laufenburg, about batteries for critical infrastructure and data centers. So this is a bit outlook for next year. So as we lost some time, I don't repeat the topic again. You're all able to read here. So I hand that directly over to Stephen Lacey, Senior Battery Scientist at Huntsman Advanced Materials. So.
Yeah, thanks, Christian. I'll just share my screen. The presentation mode. All good?
Yeah, yes, all good. I think I have a small lag. I hope the others not, but other than that, it looks great. Yeah.
Okay.
Excellent.
Okay. Good afternoon, everyone. Thanks a lot, and thanks, Christian, for the brief introduction. Also, the opportunity to speak here today at the iBAT Battery Tuesdays. So, as he said, my name is Stephen Lacey. I'm Senior Battery Scientist for the Huntsman Advanced Materials Division and working out of Basel, Switzerland. I'm also here with my colleague, Josh, who will take over the second part of this presentation. So my background is material science and engineering. I have more than a decade of experience in different material developments and battery technologies, from lithium ion and beyond. So solid state, sodium ion, lithium oxygen, lithium sulfur, thin film microbattery. I've all worked in these different fields. And for Huntsman, my work mainly encompasses R&D activities and efforts, also with product development and project management across Europe, also for different Swiss funding opportunities, as well as European funding opportunities, and technical support. So I'm customer facing, and today I'll talk on behalf as a technical expert for batteries in Europe about our Huntsman material innovations and solutions for next generation batteries. So who is Huntsman and what do we do? So Huntsman is a global manufacturer of chemical products, serving virtually every industry from transportation, construction, aerospace, clothing, fuels, energy, just to name a few. Our industry-leading portfolio consists of thousands of different products between our three divisions. So as I said, I'm from the Advanced Materials division, where typical chemistries are epoxy-based, different composites and adhesives, You might know us when you go into the local store and you see the trademark name Areodite. So it's a two-part adhesive that Huntsman creates in different epoxy resin systems. One of our sister divisions, Performance Products, they're known for their specialty amine chemistries, different maleic anhydrides, and also, especially in North America, they're also known for their high purity cyclic carbonates. So they make EC and PC that's used for liquid electrolytes and batteries. And Josh Wimble, my colleague here, is from Polyurethanes division, where he'll go a bit more in depth about the different portfolio from their side. So we at Huntsman are very committed to working directly with our customers and developing high-performance, sustainable solutions. For instance, from a battery perspective, different materials that can improve cell performance and also safety, enable next-generation technologies such as next-gen cathodes or silicon-rich anodes, also solid-state batteries, to name a few, and also different solutions we have for the battery pack and the module level that can improve and make a lightweighting or also a stronger battery box that's more protective from different aspects. And here's just a breakdown of the different products between inside the cell and more on the enclosure, so the battery box pack module level. So we broke it down. So I will start with this talk for the first 4 battery cell solutions. So MIRALON carbon materials is a unique carbon nanotube that we've seen a lot of improvement in different battery chemistries as a conductive additive, but it can also be used in a lot of different industries as well. And then from our performance products division, I'll showcase 3 specific products. So JEFFSOL, which is a NMP alternative, which is called MEOX. This is very innovative. We also want to eliminate toxic carcinogenic NMP, and we have a solvent alternative for this. There's also different polyurethaneamine chemistries with the trademark names JEFFAMINE and JEFFSPERSE that can be used for either dispersants or also polymeric modifiers to enable different binders or also solid electrolytes. And like I said before, Josh will go a bit more in depth with all these different trademark names and improvements from the battery box standpoint. So as I said, today's focus is splitting it into 2 parts. I'll take on the inside the cell, while Josh will continue with different polyurethane and epoxy solutions for battery pack protection, different composite lids, underbody protection, thermal interface materials and adhesives, as well as cell potting foams. So the first product I'd like to highlight is MEOX, which is the NMP solvent alternative for electrode casting. As we all know, NMP is very carcinogenic and toxic. So also different classifications in Europe and globally are making it a bit less easy to use and also not willing to handle. So here at Huntsman, we've created a new alternative solvent that has no CMR classification at all. It's a polar aprotic solvent, and it's used especially in the semiconductor industry and also for battery electrode manufacturing. In this case, we also have improved handling of this material, and it can be readily, PVDF and other binders can be readily dissolved into this to enable manufacturing of different electrodes. And here I just have a QR code. If anyone is interested in a bit more deep dive into the technical aspects of MEOX versus NMP, you can just use the QR code here and go in a bit more detail into our brochures. So here's a breakdown of a property comparison between NMP and our MEOX. I also put the cyclic carbonates on here just for reference. And as you can see, the main difference in structure is actually this additional oxygen, which also improves the EHS characteristics, so safety, so health and safety, but also has similar solubility parameters to enable PVDF to be dissolved within. And here we can see when you take 2 extremely well-known brands of PVDF, they both readily dissolve in MEOX as well as NMP. And when we increase the temperature to higher temperatures, obviously you have better solubility. On the right, we can see once you use this system and make an NMC slurry cathode, Here's the rheology data, where it's very similar across all shear rates, showing that the viscosity does not really change between NMP and this new alternative, which is MEOX. Now, once you cast it onto aluminum foil in this case and dry the electrode, we just wanted to ensure from a third-party validation that we still have a very homogeneous electrode throughout the entire cross-section. So we have cross-section SEM comparisons between MEOX, NMP in both NMC and LFP cathodes here. And as you can see, the distribution of all the components is very similar. There's no real difference here. Maybe if you look very closely at the LFP on the bottom right, you might be able to see a bit of a gap between the aluminum foil and the LFP cathode, which could result in the lower conductivity and also the lower adhesive strength of the NMP system versus MEOX. So on the left side, you can see that from a volumetric conductivity perspective, for an LFP cathode, we had about twice the conductivity compared to NMP. And from an adhesive standpoint, when we do a peel strength test, we also had improved, in this case, tensile strength. And from an electrochemical standpoint, in full cells, we have here LFP graphite full cells at different loadings and also at different C rates. So on the high loading cell, we have C/3, and on the lower loadings, also for pouch cells, we have 1C. The MEOX is in dark blue and the NMP is in orange. And as you can see, we have similar or slightly better capacity retention and cyclability across different loadings as well as different C rates in this case. And when you look at the far right image, the plot here, you can see that to reach the 80% cutoff, it would have more than 1,000 cycles, which means this is also an industrially relevant cell. Now I'll shift to another, essentially two product lines, so JEFFAMINEs as well as JEFFSPERSE. So JEFFSPERSE is known as a dispersant. It's typically for our inks and coatings industry. And also from a JEFFAMINE perspective, these are building blocks that can be used to functionalize different polymers and enable binders, for instance, or solid electrolytes. So with this polyetheramine building blocks, you can modify them heavily. So the tunability here is very wide. You can change the EO-PO chains and also the ratio between them to enable different hydrophilicity or hydrophobicity and different rigidity. Also, EO, so ethylene oxide, provides the ionic conductivity that you would need, for instance, in the battery electrolyte, while POD actually decreases the crystallinity. So in this case, you could have a more flexible material that can possibly cover more contact area. So in this case, I listed a couple different examples where JEFFAMINE actually modified certain polymers to be used as either a polymer electrolyte or a binder. So JEFFAMINE modified PEO also showed better cyclability, higher ionic conductivity compared to unmodified due to the different tunability. I believe this one was a diamine, which also can be cross-linked to enable different functionalities and different performance. And then JEFFAMINE modified PAN was also used as a binder. In this case, it had a very good affinity with sulfur-based cathodes as well as LFP and improved the contact area and the homogeneity in this case. And as I said, also for coatings and wettability, the hydrophilicity and the tunability of these with the different functional groups and also the amine, reactive amine groups, you can very easily functionalize and alter the chemistry and also alter the properties. So there's a lot of potential here for a lot of different things. And from a dispersant standpoint, this is actually very efficient for carbon black, a lot of different carbon blacks on the market and different carbon nanotubes, not only the one that we also produce. So in here, also for pigments and in the coatings industry, it's very important. And from a battery perspective, we also can use this particular dispersant, X3200, in both water and NMP systems to also enable dispersion and very good stability in solution. So now I'd like to shift gears to our carbon nanotube material that's very unique And the uniqueness of this comes actually from not only the production process, which is methane pyrolysis, where we're converting methane gas into this valuable carbon material as well as hydrogen. So in this case, the oil and gas industry in particular has byproduct of methane gas, which they typically flare up into the atmosphere. So you're emitting a lot of CO2. And from our process, we can use that methane from the oil and gas industry directly to create two valuable byproducts, this unique multi-walled CNT material, as well as hydrogen. So I'd like to highlight not only the properties and the morphology of this, but also how it can improve battery performance through some third-party validations, as well as also a customer success story that I've shared towards the end. So the best way to actually use our CNTs is in a dispersed form, especially for the battery electrode manufacturing, where you can plug and replace exactly the same slurry preparation steps with this MIRALON dispersion, we call it. So whether it's in water or NMP, once you disperse the material, which we do in-house in all regions, the tubules, because of this methane pyrolysis production process, it's a continuous process coming out of the reactor where you have a very long and entangled network of CNTs that are collected. And from this, once you disperse them in solvent, you can actually unroll some of the tubules into 2D sheetlets. So you have a combined 1D tubes, which are typical CNTs, and also these 2D characteristics, this network structure of sheetlets, which you can see on the right in blue, can wrap around the active material such as NMC cathodes, particles, and provide a very high electrical conductivity and pathway throughout the entire electrode. And also on the left side, we can see with an LFP cathode, you also have these very long CNT that can connect by a 1D pathway as well as throughout the entirety of the electrode. So we differentiate ourselves from standard carbon nanotubes on the market because of our sustainable process and also this unique morphology that we can enable also from our dispersion process. Now, when we go to the electrode level, we can already see improvements. So we measured electrical conductivity of both NMC cathodes and LFP cathodes with different conductive additives. So carbon black as well as graphite as a reference on the right, as well as carbon black and multi-walled CNTs on the left. So for NMC cathodes, we can see that at the same binder content, we have 4 times higher conductivity than carbon black using 1/6 of the amount of material. And when you increase to about 1/3 of the material, we can get even higher electrode conductivity, 14 times higher. On the LFP cathode, also with the same binder content, you can see that when we compare ourselves directly to carbon black, using 1/5 of the material, we have 25 times higher electrode conductivity. While when we compare us to a very industrial multi-walled CNT on the market, we also see more than an order of magnitude higher conductivity at the same loading of 0.5%. We also have data on silicon anodes, but I was not able to show it today from a third party. So in this case, we compared also directly to single-walled CNT in a silicon-rich anode where we saw also 10 times higher electrode conductivity. Now, when we are trying to enable LMFP cathodes, which also have a very low conductivity naturally, and also at different mass loadings, we can see that for LFP at a higher mass loading, we also have a noticeable improvement in volume resistivity and interface resistance. And in an LMFP cathode, when you compare it to carbon black, we also see a significant decrease in interface resistance as well as volume resistivity at a much lower loading of carbon. So you can essentially have more active material in your cathode, and it could enable higher energy densities. Now, from a thermal conductivity perspective, this is very interesting, and a lot of people don't report this. So if you think about it, especially in larger cell formats, when you have a very good thermal conductor, you can mitigate and kind of remove the heat towards the current collector more readily. And this buildup of heat, especially when you're going at high rates, could be an issue if you do not have such a good thermal conductor. So in this case, we also compared directly to carbon black as well as graphite to our MIRALON carbon nanotubes. And we can see that also because of this anisotropy, so 1D and 2D character, we have a significant improvement in the in-plane conductivity versus carbon black and graphite. So 200% improvement or 3 times higher versus carbon black with a third of the material. But also from the through-plane perspective, we also have about 1.4 times higher conductivity in this direction. And when you compare directly to graphite, which is a very well-known thermal conductor, we also see improvements, especially in the in-plane conductivity. So this also shows that this conductive additive plays more roles than just electrical conductivity. Now, when we go to rate performance, we also had comparisons from third parties such as Warwick University and WMG, where they compared single-walled CNT at a very low loading of 0.1% to our MIRALON at the same loading, and we have identical rate performance. On the right side, you can see from a EU Horizon 2020 project that we were a part of a few years back. It's called SENSE, that we're very proud to be a part of. We also had very nice data on different C rates, and across all C rates up to 10C, we have noticeably higher capacity using 1/3 of the conductive additive. From a cyclability perspective, we also saw similar or improvements. So compared to single-walled CNT at a low 0.1% loading or 2% carbon black, we had identical cycling performance in full cells. And when we compared directly to carbon black, we were also pretty similar, using a lot less MIRALON. So you have a higher active content. So when you go per cathode mass, you see in the teal and the purple line a noticeable improvement in capacity at all cycles. Now, another aspect that's innovative and useful for MIRALON carbon nanotubes is the mechanical aspect. So this network structure of tubes also enables mechanical reinforcement of the electrode, which could also enable high mass loading. So in this case, if you have carbon black only and you have a very high mass loading, say almost 30 milligram per centimeter squared, you see noticeable cracking when you wrap it around a dowel rod, so a metal rod in this case, as a qualitative example. However, for MIRALON at the same mass loading, you can go to a much lower diameter and easily wrap the coating around it without any cracking. So this shows that not only you have electrical pathway improvement, but also mechanical improvement to the electrode. And from this, during the SENSE, the EU Horizon 2020 project, one of our partners was able to do double-sided coatings, roll to roll, with 98% nickel-rich NMC, so 85% nickel, and 0.5% MIRALON, with more than 30 milligram per centimeter squared loadings. And from these different pictures, you can see that the coating was very uniform, also the distribution of particles within. And from here, we took these electrodes and they were cycled in multi-layer pouches for a long term. So in this case, we have 11.5 amp hour multi-layer pouches with the 85% nickel-rich NMC versus graphite. And you can see that after 1,000 cycles at C/3, we reached 88% capacity retention. So if you would extrapolate this out and see the capacity fade continue, we would expect 80% limit around more than 1,500 cycles. So in this case, this was a very industry relevant cell, also for automotive, which was also the target for SENSE project. And here is just the outline of all the different products that are based on MIRALON. So we have it in different forms. Our powder form is called a MIRALON pulp. While I discussed in great depth about the different dispersions, so we have both NMP and also water-based dispersions that are made in all regions. Another one that I would like to highlight is we actually have a sheet material or a tape material where you can use it as an alternative current collector. So you can replace the metal foils, conventional batteries, and see different benefits. And this brings me into the next slide, where it's a customer success story from Zeta Energy. So it's a lithium sulfur battery manufacturer. Typically, they use these batteries for drone applications, and they used our MIRALON powders or MIRALON pulp, as well as our MIRALON sheet, and improved their performance for their sulfurized cathodes. So in this slide, you can see on the right with the SEM that the network structure, the CNTs, are bridging between all the active components, which provides a long conductive pathway and also mechanical reinforcement that's needed for lithium sulfur. While on the left, you can see that due to this reinforcement and conductive pathways, you have a higher active material utilization, which improves your capacity. And this also improves the electric conductivity, of course. Now, from a sheet perspective, this is also very unique because I want to highlight that they were able to tab weld directly to our MIRALON sheet with ease. And from this, they also showed that if they replace aluminum foil with MIRALON sheet, you can have an 18% weight reduction in their 100 amp hour cells. And from this, we have a very standard voltage profile. However, the interface resistance significantly decreased with MIRALON sheet versus aluminum foil. So this highlights one success story of many, but one that I can share today about how MIRALON improves battery performance. And with that, I'd like to hand over to my colleague, Josh Wimble, so he can continue on for the second half of this.
Thanks, Stephen. Can you hear me okay?
Yeah, can hear you.
Great. Can you see my screen?
Yes.
All right. We're firing on all cylinders. Good afternoon, everyone. My name is Josh Wimble. I have the privilege of working here at Huntsman on a different division from Stephen. I work in our polyurethanes group. Today, I'll also touch on some solutions from our epoxy group, speaking for technologies out of PU and our group called Advanced Materials that has epoxies and specialty adhesives among a number of other technologies. But my focus will be on basically everything outside the cell, protective resins that keep everything Stephen just discussed going on inside the cell safe. I think many of the people on this call might be more inside the cell focused, so I'll try to keep this a little more high level on our different technologies. And please, feel free to use that react button in Teams to give a thumbs up or any indication if you want me to go deeper on anything, and happy to touch on it in more detail. Like I said, at a high level, I'll be speaking about the resins that are used in composites and foams and adhesives that help to protect the battery pack from both thermal incidents as well as the actual protection from intrusion and impact and other challenges that battery packs face. We have composite technologies that are already commercialized in a number of BEVs, fire-resistant composite technologies for interior flame shields, as well as their own inherently flame-resistant battery lids or covers, and potting foams that are one of the many inquiries that we get. Potting foams are certainly one of the more common technologies that we talk with folks in the industry about here at Huntsman. It's one of our specialties. So in the composite technology for lightweight battery covers and shields, I'm going to first start with something that's more readily out there, commercialized in a number of BEVs, which is underbody shields or underfloor protection, as it's sometimes called. So these are panels beneath the battery or beneath the valuable tray, and that tray serving many functions from load-bearing support of the battery cells or modules to cooling channels. You want to protect that from debris impact and penetration with a very lightweight but very tough panel. And for that application, polyurethane composites, especially a sandwich panel composite I'm about to describe, are ideal. You'll see these already with biaxial glass fiber composites, PU, and a sandwich with PU foam core or a long LFI, which is long fiber glass inside the polyurethane foam in a number of vehicles on the market today. That high fiber content enables an excellent mechanical performance. Lightweighting is the key, so you're going to be able to, with pretty similar protection that you get from maybe a steel sheet, see about 50 to 80% part weight reduction. So first I'm going to describe the skin part of this sandwich panel. So our polyurethane is suitable for a wide array of processing conditions. Here, I'm going to talk about wet compression molding used in the protection of these underbody shields. So first, let me, I suppose, start with explaining wet compression molding. So you can use our polyurethane technology in resin transfer molding, resin spray molding, which is already used in many roof and floor composites and automotive. It's ideal for flat, simple parts. And then wet compression molding, which is most what I'll talk about today, recommended for underbody shields and lids. Typically, you see about 2 to 3 minutes cycle times for excellent productivity. It has pretty sufficient modifiable operating life and short cure times. So at those lower temps around 40 degrees, you can have a pot life of up to 300 seconds of working time, allowing distribution of resin over very large surfaces. And then wet compression molding PU is not a very high temperature process. So for the very fast cures, you can mold at 120 to 150 degrees, save a lot on energy over alternatives. These polyurethanes also have a great balance of reactivity and viscosity for a no drip molding performance. So we use that neat skin that I spoke about a minute ago. It's a PU glass fiber or non-chrome fabric outer that bonds to the PU core material, and this neat resin has a fracture toughness of about 580 joules per square meter, which is quite high for thermosets. It's very low brittleness, high ductility and toughness, and so that with the glass fiber or non-chrome fabric makes the skin, if you will, to these sandwiches. These sandwich panels will have a foam core or LFI core. They're typically in 5 to 15 millimeter thickness, and we'll talk briefly about the trade-off in thickness and weight to get the desired impact protection. They can be molded into 3D shapes with some small angles and reasonably deep draws, so ideal for whatever aerodynamic underbody design that you have for your battery pack. Now, wet compression molding can create a fiber reinforced sheet material for overmolding the core sandwich composite structures. LFI offers a high structural support for heavy duty sandwich composites. And then foam core, which we'll talk about in a second, can deliver a really cost effective lightweight solution for sandwich composites. So this here is an example of our foam core. Between two skins, if you will. The foam core is ideal for extremely lightweight structures. You're going to go a little bit thicker, but you get extremely lightweight, cost-effective structures. It almost is just offering an air gap between the two skins for excellent impact energy dissipation. So with its strong compressive strength at 130 degrees C, this foam core can be widely used in state-of-the-art molding processes without damaging the core material as you press it to different shapes at elevated molding temperatures. For a more robust and impact-resistant option, we have LFI. This is where there's about 50 millimeter chopped glass fiber strands sprayed in with the polyurethane parts into the mold so that you have those fibers distributed throughout the foam. So this is able to enable about a 50% weight reduction for the same bedding stiffness versus the skin. So when you might think about the trade-off is if the skin thickness for the foam core is kept level of the LFI configuration, but the core thickness of the foam is doubled versus the LFI core, then the bending stiffness is about 2.5 times increase. But the weight is about 37% of the monolithic one only. So selecting between the two really depends on your thickness and weight trade-off. Basically, you can get a thinner, more durable part with the LFI core, but you can get a lighter weight, more cost-effective part with the foam core. What's really exciting to me about these technologies is how they can be leveraged in a single layer glass fiber or non-chrome fabric composite for battery lids. So we have what we call our Vitrox wet compression molded polyurethane system that's designed to meet outstanding flame performance requirements. So as you can see in this table here, as thin as 1 millimeter with the glass mat can achieve UL94 V0 and 5 VA. And at 3 millimeters, this can meet some pretty aggressive cycles of UL2596. I think most folks are probably familiar with it, but it's the direct torch at 1200 degrees Celsius, blasted with superheated metallic debris in various cycles. And the results that we're seeing in the pending testing from non-chrome fabric also shows outstanding performance. Some of our customers, through their simulated UL259.6 tests, have seen even more cycles passed at 3 millimeters than we have in our 2596. So it's really promising as not just a mica alternative, but because this is a self-supporting semi-structural composite, you can potentially enjoy those molding benefits, those quick process times of under 3 minutes that I talked about, while not requiring an additional heat shield or thermal barrier potentially. You're probably aware that aluminum and many thermoplastic composites or sheet molded compounds, except those in the higher range of price, they burn through quickly in UL2596 without a mica shield within the battery pack. The Vitrox wet compression molded materials present an option for something that's inherently flame resistant, so you're not only getting the part weight savings of using a composite, but you're potentially also able to get the cost savings of consolidating the two parts into a single lid. Similar composites are also used in China for resin transfer molding. I specify China because that's where the majority of this equipment is already in place for the resin transfer molding process. I won't go into a lot of detail about this, but at a higher level, this provides a wider variety of structure. You can see there's more complex structures and shapes that are more easily molded in faster cycle times, but just not as extreme flame performance. So these are typically rated for up to UL94 V0, but not promoted to be used as the primary flame-resistant component of a battery pack, ideal for the lightweighting and fast cycle times. So then as we go from, we talked about the underfloor protection, we talked about the battery lid. As we go further in, I should also mention too, sorry, I got ahead of myself. We have epoxy resins as well for composite lids for battery housings. With similar flame performance, UL94 V0 solutions, many of them also able to meet UL2596 requirements for multiple cycles. These are a really robust range of resins from our advanced materials team for more intrinsically flame resistant concepts, all the way to even some sheet molded compound concepts for more complex shapes. I'll just highlight that one of the advantages of working with Huntsman is that we have both these teams in-house. So no matter which technology you're looking at for wet compression molded or other molding processes, if you're looking to do thermosets, epoxies, polyurethanes with glass fibers, non-chrome fabrics, or even carbon fibers, our teams have pretty diverse experience here and are great to talk to early on in your process as you're considering what kind of material as well as what kind of molding technology you want to move ahead with. Okay, so now I'm getting to the potting foams, which is what people most often come to us about because of our success in this field. So cell potting foams, or sometimes they're called cell encapsulation resins, they serve a really different function depending on who you're talking to. So most use them for some level of mechanical fixation or vibration damping of cells, especially with cylindrical cells. They're great at being a very processable, very manufacturing friendly solution for pouring in and quickly curing and keeping your cells protected. Some OEMs use them to improve the pack or module stiffness, so use higher stiffness foams that can contribute to the mechanical properties of the overall pack. While many focus very specifically on the resin's role in mitigating thermal runaway propagation. So we have a broad range of systems. If you're interested in seeing some of the available systems we have, please follow up with us. Here, I'll just highlight that most of ours are extremely low thermal conductivity with good dielectric properties above 6 kilovolts per millimeter. Most cure within 20 minutes, 30 minutes at most. And by cure, I mean they're stable and able to be moved or rotated without the resin moving. It's basically formed completely. Clamp time, some might call that cure time. The cure continues over days, as it does with all polyurethanes, but the workable time for potting a battery pack is typically 20 minutes. And that's great cure times, considering that these battery packs basically act as a heat sink. So when you're pouring in a material that typically reacts faster and better with heat, all that metal in the pack is pulling away from it. One of the great things about working with Huntsman is that we have many in-house dummy kits imitating different pack designs, as well as different cell diameters and different materials that you might use for those packs and cell shells. And so our team can readily imitate and trial out different systems to make sure we have the right one for your design physically as well as through our simulation. When I talk about simulation, I mean, we have an outstanding team that supports with digital simulation of flow, fill, leveling of different systems within your battery pack designs. Now, everybody's battery architecture is really different. We haven't gotten to a great place of harmonization yet in this industry because this is an area for a lot of differentiation. So we select the right viscosities and reactivity profiles for a range of considerations, including the tight spaces that this resin has to flow through. There's narrow cell gaps, potentially cooling elements. Our team can advise on the optimal pour points in the battery pack, and they can even support you in characterizing how different mechanical properties will affect your full pack integrity if you include us early enough. Some people are designing their battery modules and packs to take advantage of the stiffness of the foam itself. We also support our customers in running through thermal runaway analysis. This is really challenging since there's no consistent test, OEM to OEM, or even consistent nomenclature or acceptable metrics in this space. So it takes a lot of learning as you go. And fortunately, we have a team with as many years of experience as you can have, given how relatively new this segment of the industry is. One of the things that we get often asked about is about flame performance of our potting foams because it's perceived to have a role in thermal runaway mitigation. Now, our team that runs our simulations has done quite a bit of analysis to determine what are the more critical properties from our perspective in mitigating propagation. So while many people, the first thing they might ask is what's the UL94 flame rating of a particular foam? It's the auto industry. It's a rating we're familiar with. We find it doesn't really have a perfect correlation to performance in this area. I've witnessed two different systems, one UL94 HB system up against a UL94 V0 system at an OEM where they're in a battery pack where the system that was rated for horizontal burn rather than the full V0 actually prevented flame escape for many minutes longer than the V0. And that's because the flame rating alone isn't a perfect indication. We found that diffusivity, that is finding the right density target and the right thermal conductivity of the material to prevent heat spread, is a pretty significant factor. So in some cases, adjacent cells may be overheated from ambient temperature of the cell that's going through the thermal event, through the incident, before the flame even touches it. And so that might set off the adjacent cells before the flame is even necessarily a factor. So insulating that heat, isolating it to this particular area is key, as well as thermal stability. So you want these potting resins to form char, but also maintain their structure. So the quicker the resin wears away, the worse that typically is for thermal runaway mitigation. Now, our resins typically aim to achieve less than 0.5% reduction in weight by the time it's reached 250 degrees Celsius sustained. And now all of this is something that these are just recommendations and observations. These are things that our team works very closely with OEMs and battery module makers to identify the right polyurethane system for their targets. Everything is a little bit of a trade-off between cost and performance, processing, and so this is an area where our team of experts very closely engages a wide range of engineers at the customer to identify the right polyurethane system for their requirements. The final area that we're in the polyurethane space is thermally conductive adhesives for battery packs. Here we have an example of our aerothane thermally conductive adhesives. We also have epoxy adhesives for underfloor panels and covers, as I mentioned, and encapsulation for protective sensitive high voltage components like power electronics. This is an example of our 1.8 watts per meter Kelvin thermal conductivity system. Now, you see a range of thermal conductivity specified. Thermal conductivities are pretty modifiable based on target properties. It's all a trade-off. Our advanced materials team will work closely with a battery module maker or OEM to identify the optimal thermal conductivity while also optimizing strength, processing, and costs. And processing and costs are areas where you have to be pretty sensitive with the overuse of fillers. So it's about working with the experts on our advanced materials team to find the right solution for your specific application. The team is very proficient at developing adaptable open and curing times to support production flexibility. They've got really close relationships with a number of dispense equipment suppliers. So if you reach out to us about your specific thermal conductivity requirement and your adhesive requirements for your design, our team can also connect pretty quickly and pretty early in the development cycle with the equipment suppliers to optimize for your conditions, even make recommendations if you aren't at the point of having already sourced your equipment as well. You can see down in the bottom right, there's a video of the dispense of the thermally conductive adhesives. One last technology I'll mention that's emerging as a priority for some development teams with the changing of requirements around thermal runaway in China. To give a bit of context to that, I think a few people have heard there's this proposal in China to move from what's typically globally anywhere from 5 to 15 minutes of escape time to up to 2 hours of escape time, where a battery has to completely maintain a thermal runaway event for 2 hours. It's a pretty significant jump. And so the industry is looking at a variety of technologies that can help support this. Huntsman already has a fast curing intumescent coating system that's found success in some other markets that are extremely sensitive to flame. I won't go into a lot of detail about this. If it's something you'd like to talk about, please follow up with us. But this is a technology that can be sprayed onto just about any composite surface and pre-treated metal surfaces that has 100% solids, very low VOC, low emissions. It's a very tough and flexible system that is designed to be sprayed on and provide really intense thermal protection. So when I say fast cure, here's the spray onto a vertical surface. And as you can see, he touches it right after spray, wet, and then immediately dry, not transferring any residue after about 3 seconds. So very quick cycle times with this technology, can be sprayed into a variety of applications. I'm not going to show you this whole thing, even though it's sped up. This is still about a 4-minute video and we're near the end of our time. But I want to just skip to a few points to show how this intumescent coating begins to swell and form a protective barrier to mitigate the active flame threat that's going on here. Very low expansion pressures here. So it's not necessarily a damaging swelling process. It's one that helps to form an insulating char and reduce the impact of the flame on the surface that it's adhered to. You can see at a certain point, it maintains this char consistently. On the left, you can see the temperature graph. So even after an hour, there's still not failure from the different materials. And typically, it doesn't for the first 30 minutes exceed the 250-degree mark when exposed to this flame well over 750 degrees, escalating to almost 1,000 degrees Celsius. So it's a very interesting technology for different more sensitive areas of the battery pack as people rethink how they're designing for these much more long-term testing parameters coming out of China on escape times. Oh, showing it to me again. How do I skip through this? There we go. So I just took us through at a high level. I noticed I didn't see any reactions or hands raised, so I hope I covered it to the degree that is relevant for this audience. Again, our contact information is here, so please feel free to reach out if you'd like to talk to specific engineers to go into detail on any of those pack protection resin systems. Stephen, any final comments from your end?
I mean, I see a couple questions in the chat, but
I must not have that view set up. Hang on.
Yeah, I think the questions were addressed to you, Stephen, as mainly about the PVDF. So maybe if you read already, you can start answering those questions. Yeah.
Yeah. So, like I said, our JEFFAMINE chemistry is very diverse. We have a lot of different opportunities, and actually, Professor Armand, so from CIC in Spain, he also went and did a lot of analysis from an academic standpoint for industrial purposes, where he identified a lot of different JEFFAMINEs, specifically the diamines, that could be used to modify to make different binders. So yes, we've tested some performance, both internal and also, for instance, at Professor Armand's group. And we're also interested in also collaborating if I think Darina was the one who posted that one. Yeah, of course, like I said from the beginning, sustainability is a big topic for Huntsman. We pride ourselves on this to also give sustainable solutions. So we're very open to collaboration as well.
I was wondering, I mean, I'm really spoiled by the improvements in conductivity that you show with the CNTs, right? On thermal, but of course on electrical side. Um, uh, what are the impact on the recycling process? Because you say like sustainability is important, and yeah, like I think this is still a bit an open point. Or what's your standpoint on that?
I mean, a lot of the recycling is mainly focused on the more, I would say, profitable portions of the battery cell. So a lot of focus is mainly on the active materials and trying to extract like nickel, cobalt, manganese. At the moment, we do have some third parties that are doing some recycling efforts, but I think typically the carbon would just kind of be burned off.
Yeah, I think my question was more towards yeah, like from the like CNTs are kind of sensitive, right, and already to deal in the production environment, but for even more for a recycling environment. That was more my standpoint than to recycle the CNTs itself.
Mm. Yeah.
Well, I don't know if there are other questions from the audience. I don't see anything else in the chat. I was just wondering on slide 13 when you showed us the MEOX. This was like slightly worse on C/third and better at 1C. Do you have any explanation on that, or is that just within like basically like the tolerances that you measured or analyzed the different compositions?
If I remember correctly, 13 was also different mass loadings. So that could also be why there was slightly different values there. Yeah. And then I see in the chat about, I guess since we're talking about MIRALON, maybe I answered the multi-weld CNT. So all the data that I showed was actually MIRALON by itself, no actually carbon black or other additive inside. We've seen very good performance with this. When you add carbon black, you need to be a bit more careful with the mixing procedure, so the slurry preparation, to get a very homogeneous electrode slurry. So I also developed a slurry mixing protocol specifically for our dispersions to help customers with this. So if you believe that you need carbon black, then I can guide you on how to combine it. But a lot of the time we see similar or better performance when you have MIRALON by itself. And then for the MEOX market adoption, so I can actually, if you reach out to me directly, I can forward you on to my colleague Thomas in HPP division. But so if you noticed, there were a few parameters that were a bit higher temperature, so like higher boiling point than NMP. So in one way, you do have to put a little bit more energy from the heating perspective to dry your electrode. However, the most unique part of this is actually the recovery system. So NMP recovery, solvent recovery, is typically the most expensive battery electrode manufacturing portion. It's almost even 40% of the cost. In this case, we've done both modeling and also some testing where we can use the exact same equipment as NMP, so it's a plug-and-place replacement. But the condensation process is actually much simplified. So you can actually, instead of a two-part or even a longer two-step, three-step process, you can go down to only one condensation step to actually recover the MEOX. So in this way, you actually save a lot of cost in manufacturing.
Well, excellent. I would say once again, thanks a lot to Josh and to Stephen for the deep insight. I think it was a very interesting Battery Tuesday today. Still very nice to see that there are improvements even for what we may call now standard lithium-ion batteries, LFP, NMC. So thanks for that. We see each other in a month. We will have then the Touring Club Switzerland, so very other topic, very high level. I think that's the essence of iBAT, to create an understanding between each other. Hope to see you there again. Thanks a lot, and see you on the next Battery Tuesday.
Thank you for the invitation and for your time. Appreciate it.
Likewise. Thank you, everyone. Have a good day.